Notes 1 and 2 of the National Electrical Code Table 220.19 provide guidance on calculating feeder demand for electric ranges. Understanding these notes is crucial for accurate electrical calculations, especially when dealing with ranges rated over 12 kilowatts. Note 1 addresses the concept of a major fraction. A major fraction means over 50%. If the rating of an individual range exceeds 12 kilowatts by more than 50%, increase the feeder demand by 5%. This 5% increase is applied to the ranges rated over 12 kilowatts. Note 2 clarifies that the 5% increase applies to ranges rated over 12 kilowatts, regardless of whether they are connected to a single-phase or three-phase service. Let's consider some examples. Firstly, a 12.8 kilowatt range. 12.8 kilowatts is over 12 kilowatts by 800 watts, which is more than 50%. Therefore, increase the feeder demand by 5% for this range. Secondly, a 12.5 kilowatt range. 12.5 kilowatts is over 12 kilowatts by 500 watts, which is not more than 50%. Therefore, do not increase the feeder demand by 5% for this range. Thirdly, an 11.6 kilowatt range. This is irrelevant for the feeder demand calculation because it does not involve ranges rated over 12 kilowatts. To calculate the total feeder demand, you would sum the ratings of all ranges, applying the 5% increase where applicable based on Note 1. Let's apply these rules to a specific question. What is the feeder demand for 12.8 kilowatt household ranges, 12.5 kilowatt ranges, and 11.6 kilowatt ranges if connected to a three-phase service? The term household range typically refers to a range used in a residential setting. The term range generally refers to a cooking appliance with multiple burners and an oven. The question involves a three-phase service. However, the table you are referring to is for single-phase service. Therefore, you cannot directly use the table to find the answer. Instead, you need to calculate the feeder demand manually. The feeder demand is the sum of all range ratings. Feeder demand equals 12 times 12.8 kilowatts plus 12 times 12.5 kilowatts plus 24 times 11.6 kilowatts. This equals 153.6 kilowatts plus 150 kilowatts plus 278.4 kilowatts, which totals 582 kilowatts. Note that the 5% increase may or may not apply to the individual range. The 5% increase is applied to ranges rated over 12 kilowatts, regardless of whether they are connected to a single-phase or three-phase service. Now let's address some potential points of confusion. One common issue is understanding what constitutes a major fraction. As mentioned earlier, a major fraction means over 50%. So, if a range exceeds 12 kilowatts by more than 50%, the 5% increase applies. Another point to consider is the difference between a household range and a range. The term household range typically refers to a range used in a residential setting, while the term range generally refers to a cooking appliance with multiple burners and an oven. In most cases, the terms are used interchangeably for calculation purposes. The feeder demand calculation is independent of whether the service is single-phase or three-phase. However, when determining the appropriate conductor size for the feeder, you will need to consider the type of service. For a three-phase service, you will need to calculate the current in each phase and select conductors that are appropriately sized for the calculated current. To correctly perform the feeder calculation, firstly, identify all ranges that are rated over 12 kilowatts. Secondly, for each range rated over 12 kilowatts, determine if the excess over 12 kilowatts is more than 50%. Thirdly, apply the 5% increase to the feeder demand for each range that meets the criteria in Step 2. Fourthly, sum the ratings of all ranges, including the 5% increases, to determine the total feeder demand. Fifthly, if the service is three-phase, calculate the current in each phase based on the total feeder demand. Sixthly, select conductors that are appropriately sized for the calculated current, taking into account ampacity, voltage drop, and other relevant factors. Let's look at another example. Suppose you have 10 ranges rated at 13 kilowatts each. Each range exceeds 12 kilowatts by 1 kilowatt. Since 1 kilowatt is more than 50% of 12 kilowatts, you would apply the 5% increase to each range. Feeder demand for each range would be 13 kilowatts plus 5% of 13 kilowatts, which is 13.65 kilowatts. The total feeder demand would be 10 times 13.65 kilowatts, which is 136.5 kilowatts. Another example, suppose you have 5 ranges rated at 12.4 kilowatts each. Each range exceeds 12 kilowatts by 0.4 kilowatts. Since 0.4 kilowatts is less than 50% of 12 kilowatts, you would not apply the 5% increase to each range. The feeder demand for each range would be 12.4 kilowatts. The total feeder demand would be 5 times 12.4 kilowatts, which is 62 kilowatts. The National Electrical Code provides specific requirements for conductor sizing based on the calculated feeder demand. Refer to the appropriate tables in the NEC to determine the minimum conductor size required for the calculated load. Remember to consider factors such as ampacity, voltage drop, and the type of insulation when selecting conductors. The NEC also addresses the use of demand factors for various types of loads. Demand factors are used to reduce the calculated load based on the assumption that not all loads will be operating at their maximum capacity simultaneously. Demand factors are typically expressed as a percentage. When applying demand factors, multiply the calculated load by the demand factor to determine the reduced load. Use the reduced load to size conductors and overcurrent protection devices. For example, if a demand factor of 75% is applied to a 100 amp load, the reduced load would be 75 amps. In addition to the NEC, local codes and regulations may also apply to electrical installations. It is important to consult with local authorities to ensure compliance with all applicable requirements. Local codes and regulations may be more restrictive than the NEC in some cases. The term kilowatt is a unit of power equal to 1000 watts. The term watt is a unit of power equal to 1 volt times 1 amp. The term volt is a unit of electrical potential difference. The term amp is a unit of electrical current. The term ohm is a unit of electrical resistance. The relationship between volts, amps, and ohms is described by Ohm's law. Ohm's law states that volts equals amps times ohms. The NEC provides tables for determining the ampacity of conductors based on their size, type, and insulation. The ampacity of a conductor is the maximum current that the conductor can carry continuously without exceeding its temperature rating. It is important to select conductors with an ampacity that is greater than or equal to the calculated load. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC provides guidelines for limiting voltage drop in electrical circuits. The type of insulation used on a conductor affects its ampacity and its suitability for different applications. Common types of insulation include THHN, THWN, and XHHW. Each type of insulation has different temperature ratings and resistance to moisture and chemicals. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect electrical circuits from overloads and short circuits. Overcurrent protection devices are designed to interrupt the flow of current when it exceeds a predetermined value. It is important to select overcurrent protection devices that are appropriately sized for the conductors and equipment that they are protecting. Short circuits occur when there is an unintended connection between two conductors of different potential. Short circuits can cause a large amount of current to flow, which can damage equipment and start fires. Grounding is the process of connecting electrical equipment to the earth. Grounding helps to protect people from electrical shock and to prevent damage to equipment. The NEC provides specific requirements for grounding electrical systems. Bonding is the process of connecting metal parts of electrical equipment together. Bonding helps to create a low impedance path for fault current to flow back to the source, which helps to trip overcurrent protection devices. The NEC provides specific requirements for bonding electrical systems. The electrical safety is of paramount importance. Always de-energize electrical circuits before working on them. Use appropriate personal protective equipment, such as gloves and safety glasses. Follow all applicable safety procedures and regulations. If you are not qualified to work on electrical equipment, hire a licensed electrician. Remember to consult the latest edition of the National Electrical Code and any applicable local codes and regulations for the most up-to-date requirements. Electrical codes and regulations are constantly evolving to reflect new technologies and safety standards. Staying informed about these changes is essential for ensuring safer and compliant electrical installations. The information provided in this narration is intended for educational purposes only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician before performing any electrical work. Working with electricity can be dangerous, and it is important to take all necessary precautions to protect yourself and others from harm. By understanding the principles and practices of electrical safety, you can help to prevent accidents and ensure the safe operation of electrical systems. Remember to always prioritize safety when working with electricity.